Thanks, Alan. So I suppose I'm going to shift to the other end of the age spectrum here compared to what Johan and Josh were talking about, towards some of the younger rocks in the Eastern Fold Belt. So today there's plenty of things that I could talk about for the Tommy Creek block, but we'll do a quick look at where we are and what the regional geology is for it. Some of the previous work that's been done in the area, and then go through some of the geochron and the revised framework that I've come up with over the last couple of years. And then a quick tour of some of the weird and wonderful rocks of Tommy Creek, some rather unusual lithologies, some unusual outright, and others are more unusual due to them not being particularly recognised in the Mount Isa inlier before, and maybe some of the implications of those. So the Tommy Creek domain is the smallest of the tectonostratigraphic domains in Mount Isa inlier. It sits in here, wedged up in between the Mary Kathleen domain, the Kenobi domain, and the Midikudi domain. And it's bounded by large-scale structures, particularly the Fountain Range Pilgrim Fault Zone to the west. It's thought to have the youngest stratigraphy within the Eastern Fold Belt, often interpreted in a lot of the GSQ publications at around 1620 million years. It also has pre-orogenic felsic intrusions that aren't related to the burstal suite, amphibolite facies metamorphism, complex deformation, and it's often bypassed in broader Mount Isa studies. It's often been lumped into the too hard basket, I think. And it probably isn't helped by the fact that there's no current operating mine, so it's maybe not as sexy as the Selwyn domain with Cannington, or with Osborne, Soldier's Cap with Cannington, and the Kenobi domain with Ernest Henry. But there is historic production there. So Federal Mine was actually the largest producer of copper in the 20s and 30s in the region. And that also has some associated cobalt mineralization. And we also have GBM's Milo undeveloped deposit of copper and rare earths. We also have quite a number of occurrences of rare earth mineralization, obviously at Milo, but at some lesser known prospects, Beacon, which is a fluorite deposit with uranium and rare earth credits, the brown snake rare earth occurrence, and also the boundary rare earth occurrence. So these are some interesting things to consider in the context of what I will present coming up. So a quick zoom in to most of that tectonostratigraphic block in the current 100,000 mapping. And some of the major elements that we have in the regional geology here is in blue, the Corella or Staveley equivalent calc-silicates and the 1650 Tommy Creek microgranite. We have a wedge of Bolonga volcanics in here along the eastern margin of the block. And then we have these young Milo beds sitting in two separate basins in the central area, which are the youngest parts of the sequence. So if we look at our time-space plot of the Mount Isa inlier, these Milo beds sit up here all on their lonesome in the Eastern Fold Belt with ages younger than 1640, potentially as young as 1615, which is post-Soldier's Cap group and all their equivalents, and actually puts it out more towards the Eisen supergroup and the Lawn Hill stuff in the west. So we started some exploration out here in earnest between 2014 and 2017. We knew it was pretty complicated and interesting out there. We did some mapping, some drill targeting the silicious Goshens over significant strike lengths and their associated surface geochem. And while we were doing this, we saw all sorts of other bits of interesting geology. So we saw fractionated, or differentiated, sorry, ultramafic mafic sills, quite a bit of variation and complexity within the felsic rocks that wasn't previously recognized, magmatic breccias, exceptionally graphite-rich schists. So we were getting up to 25% total graphitic carbon in these rocks. Potential alkaline magmatic rocks, cyanites, glimmerites, and lamprites. Extensive intrusive carbonate, which we now believe to be carbonatites. extensive sulfide and magnesian alteration system, and a lot of weird lithogeochem, particularly in the immobile and high field strength elements. So I embarked on a part-time PhD to try and sort at least some of these problems out. And ultimately, we want to understand what the ramifications of any or all of these could be for mineralization in the region. So I've got a picture there, which is a sillimanite graphite schist, which that interval there is probably running about 18% graphitic carbon. So here's a simplified snapshot of the mapping for the area. The main things to take away from here is we have multiple deformation episodes. So we have an east-west fabric and a more or less north-south overprinting causing our macro scale folds. And the younger Milo beds, which are in the browns and greys, are separated from the Corella Formation equivalent calc-silicates, probably through quite a significant structural unconformity. So we saw geochronology as a key part of this project. We wanted to try and pull apart some unresolved questions from the original work done by Rod Page and June Hill in the early 90s. Are these actually Corella Formation equivalents, or are they young calc-silicates? Are the Milo beds as young as we say they are? All those sorts of things. So we targeted various magmatic phases and also some detrital samples. And we were pretty ambitious with some of these, particularly in the mafics. So it was unsurprising that we had quite a number of failures there. So in total, I attempted 60 samples and we got just over 30 successful ages out of those 60 samples. What was really surprising was that a number of our really promising samples, so we had some volcanic horizons high up in the graphitic schist stratigraphy, running 1,000 ppm zirconium, as well as some high zirconium dolerites, again around 500 to 600 ppm zirconium in whole rock. Utterly failed. Not a single zircon could be pulled out of them. And it wasn't until we got them under the SEM that suggested these were tiny, sort of 1 to 2 micron size zircons hidden as inclusions throughout rutile, feldspar, and amphibole. So the results weren't always clear, but they certainly changed the way we thought about some of the things. So here I've got a schematic representation of how I think the various lithologies of this central Tommy Creek area relate to each other. So we have the Staveley or Corella equivalent calc-silicates essentially forming a basement, which is structurally separated from the younger Milo sequence. We have the Tommy Creek microgranite intruding in at about 1650. And this is actually cut by this structural unconformity. We then have the lower sequence, which in a lot of the earlier work, particularly by June Hill, were referred to as the Tommy beds. These are massive and volcaniclastic felsics, as well as feldspathic siltstones. One of the interesting things that we got out of the geochron was that these porphyries intruding in about halfway up the sequence were actually a 1640 age, which has some pretty key factors in how you pin the rest of the sequence. We also have the Carbonatites coming in at a similar time. We then have the upper sequence Milo beds, and this intrusive position of the quartz feldspar porphyry appears to almost mark a change in the sedimentary character of the sequence, and we shift more into churchy siltstones, biotite siltstones, and then finally our graphitic schist and peolitic schists at the top of the sequence. We then have later intrusions, dikes and pegmatites between 1620 and probably through to 1525. So these have got various felsic compositions, as well as glimmerite, granitic pegmatites, cyanitic pegmatites, and a layered pyroxenite gabbro sill. So I'll just go through some of these in a bit more detail with the ages. As I said, we got a nice detrital spectra out of the calc-silicates with the maximum depositional age of 1747. This is pretty consistent with the Corella Formation and the Staveley Formation, suggesting that these are not young calc-silicates within the Tommy Creek block, as was postulated at some point by people like Blake and Derrick. We also have lower parts of the sequence here with maximum depositional ages around 1660 or mid-1650s. And then we have the intrusion of the quartz feldspar porphyry. We've got 3 ages with pretty good agreement at around 1642, and our intrusive carbonate or carbonatites with very similar ages. Ironically, these are actually, in many cases, better looking dates and more concordant data than the felsic rocks pulled out. We also have marbles which sit in this same piece of stratigraphy with zircon populations such as 1650 and 1725, these being max depositional ages. We shift into the upper sequence and the younger intrusions. So I found this really interesting. In the top of our graphitic schist, I did manage to get a max depositional age of about 1640. So we have sedimentation occurring at the top of the sequence at about the same time as we have the intrusion of the porphyry sills lower down in the sequence. We have this suite of felsic intrusions all coming in at around 1615 to 1610. So these are probably immediately prior to the start of the Eisen orogeny. We also have our pegmatites, the cyanitic pegmatites and the glimmerites. These ages aren't very good. I think the general chemistry of the rocks has played havoc with the zircons, and we have some closure problems and stuff like that. But the best indications is that they're also at approximately the 1615 age. I got really lucky. I had lots of mafic rocks which failed, but I had one tiny little basaltic dike which cut through the gabbro sill. It was about 40 centimeters of quarter core, and I managed to get 60 zircons out of it, which was really lucky, at a really nice age of 1617. So that gives us a bit of a lower limit on one, when the gabbro is intruded, and also the sedimentation of the entire sequence. This biotite porphyry or gneissic rock, which is also really important because the GSQ sampled a very similar looking rock. I visited their sample site, found where they'd broken off, where Ian had smashed the rocks to smithereens. And it's essentially the same rock, a sort of biotite gneissic looking thing. Stratiform, and I got exactly the same age. But the field context in the central Tommy Creek area suggests that it can't be interpreted as a volcaniclastic, as it has been previously by Ian and I think it was Chris Carson. And this is, in fact, an intrusion age. So I think we can probably pull back that really young, lower constraint on the Tommy Creek, and that it probably needs to come back to about 1625 or 1630. Also for context, I forgot on the previous slide, so these ages here, 1650, 1660, this puts it equivalent to the very top parts of the Tall Creek volcanics and equivalents in the Young Albert group and that sort of stuff. And then finally, we also did some Titanite ages with the alteration, and I think I would have to echo what Johan said about Titanite ages. It seems to be that wherever you go, you get this 1525, but I also got some others, and there's some really interesting samples in here, particularly this one, where I have a 1525 age out of a single grain. This grain's about 5 centimeters across, from the same interval that included that large megacrystal. I have a multi-grain age of 1550, and not a single indication of a 1525 age in those smaller Titanites. So there's a lot going on, and it's a lot harder to interpret these Titanite ages. So with that, we'll switch across into maybe some of these more unusual lithologies that we're seeing in the Tommy Creek block here. So the first one up is the Carbonatites. So we first noticed these in the 2016 drilling as veins of calcite and biotite with minor amphiboles. The assay suggests these were very magnesium rich, so the carbonate is probably dolomitic, and the biotite's towards the end of the phlogopite end of the spectrum, and we later confirmed that with microprobe analysis. The phlogopite was often more pronounced towards the contacts, And then when we drilled further in 2017, we actually showed up some much larger bodies of these, some greater than 5 meters across, as well as continued finding these small veins. We had prominent phlogopite reaction rims with the wall rock and xenoliths of quartz feldspar porphyry within them, which is what the image here is. So we've got some altered feldspar porphyry with a phlogopite reaction rim within the carbonate rock. And also its relationship to the magnesian amphibole alteration within the siltstone started to become a bit clearer, which I'll show an image on the next slide of. The petrography suggests the textures of these rocks are possibly igneous. They're quite different to the normal dirty and ragged carbonate that you see in marbles and other hydrothermal carbonate veins in the Eastern Fold Belt. And lots of zircons and apatite, particularly in and around the phlogopite grains when you're looking at the petrology. So here we have an example of a really sharp contact between the carbonate rock and the metasilt stones. And we also see this related alteration. So we've got a total replacement. This here is tremolite and sericite. And then we also have a partial replacement and bleaching, which is also largely sericite and tremolite working its way into the siltstone. We also have, towards the margins of one of these larger dike bodies, clasts of the wall rock, in this case, the quartz feldspar porphyry being ripped off and entrained within the carbonates. So they're really cryptic at surface. The smaller veins obviously are rarely seen, and the Tommy Creek prospect area itself is quite leached and silicified at surface. And as you can imagine, these things just look like marble that we're really used to seeing everywhere in the Eastern Fold Belt. There isn't any great obvious geochem or oxygen isotope differences. This is a bit disappointing, but when you look into it a bit closer, it's also not necessarily surprising. The carbon and oxygen isotopes are within the range of your global carbonatites. They actually sit really close to places such as Phalaborwa in southern Africa. However, the Eastern Fold Belt carbonates also show an alteration overprint, which has a reservoir with very similar values to these, which was work done by Lucas Marshall and Nick Oliver in 2006. So it's possible that these rocks have seen this alteration, but because they already started at that point, they just haven't moved any further. The samarium neodymium isotopes are also compatible with the literature, but they don't have the strong mantle signature of, say, some of the really young East African rift carbonatites. And for me, other than the field relationships, the zircons turned out to be key. So we had single coherent populations of zircons within the carbonatites compared to the multi-population spectra that we would see within the marbles. And the carbonatites also gave us really nice concordant ages. They also had a distinct trace element signature. So here we have a spidergram just with zircon trace elements by laser ablation, normalized to C1 chondrite. In the blue here, we can see the zircons that I ascribed to being carbonatites, and we compare those to the pink traces here, which came out of the marbles. We can see a clear difference, particularly in the light rare earths. Also encouraging was that zircons out of the lower sequence volcanics also shared the same chemistry as the marble, suggesting a similar provenance for those detrital zircons. Crucially, there is a big difference both in the light rare earths as well as in niobium between the carbonatites and the same age porphyries at 1640. So these are not zircons that these have inherited from their host rocks. They're completely different zircons. And what will become, I'll elaborate on in a bit more, is that the 1610 porphyries also have very distinct zircon chemistries compared to the 1640, particularly up here in the heavy rare earths, as well as in the high field strengths and the light rare earths. So the next unusual lithology is Glimmerite, which is a term for an ultrapotassic rock, which is composed primarily of biotite. So here at Tommy Creek, they're mostly coarse phlogopite with K feldspar, some iron carbonate and fluorite. Interestingly, the fluorite actually mostly appears as an intramineral cleavage replacement, which we can see here in this photomicrograph. These aren't veins cutting across the rock. These are held within single grains of phlogopite between the crystal layers. So this suggests to me that perhaps this magma was pretty saturated in fluorine at its emplacement, and with a bit of a kick through metamorphism, it started to boot out the fluorine and it's had to go into fluorite afterwards. And there's lots and lots and lots of small zircons all throughout these phlogopites. They're absolutely pitted with pleochroic halos. Also got some pegmatites, which in their own right aren't all that unusual for the Eastern Fold Belt, except for perhaps this bottom one here, the cyanitic pegmatite, which is a very coarse K-spar phlogopite, sodic amphiboles, as well as these really late, huge titanites, which get up to 10 centimeters across. We've also got some lovely big coarse feldspar pegmatites, and I don't have an image here, but we've also got some nice hypersolvus graphic textured pegmatites as well. And finally, we've got our Mafic-Ultramafic Sill. So we noticed this as a fairly prominent mag feature in a nickel-chromium soil anomaly. And it turned out it was a multi-compositional sill ranging from a fine foliated chlorite magnetite schist to a coarse hornblende gabbro. Chlorite schist was extremely magnesian. It's running about 20% MgO. And when we started to have a look at these things in thin sections, we started seeing serpentine, talc, olivine, and some interesting composition amphiboles. So we think this was probably an olivine-bearing pyroxenite in its original form. And it is the source of the magnetic feature, but the magnetite itself is a local effect and doesn't always form in this rock, because we found a much larger extent of this chlorite schist that's not magnetic. It intrudes into the graphite schist. It's pre-deformation and pre-metamorphic peak, and it's cut by this 1618 dike. It's locally garnet bearing, sometimes up to the size of your fist. And we also have some chemical suggestions that these have enriched morb affinities. And more recently, we got some neodymium samarium data, which suggests this is the most primitive source magma in the Eastern Fold Belt. So we'll look at that a bit more carefully now. So I've done both whole rock neodymium samarium as well as zircon, hafnium, lutetium isotopes, and they both tell very similar stories. So here we have the Mafic-Ultramafic rock sitting up here at, I haven't drawn on the primitive mantle evolution line here, but quite close to it, and compare that to other rocks within the Eastern Fold Belt. So we have the Chalcodene-Leichhardt belt sitting here, Tool Creek volcanics, and these are all just mafic rocks, and mafic rocks associated with the Williams suite are all considerably more juvenile. So the only thing that comes close are some Archean fragments within the Black Angel gneiss and the Chalcodene-Leichhardt belt. The young porphyry, so the 1610 porphyry, is also surprisingly primitive, sitting here in the pink dots, compared to all the other felsic phases within the Eastern Fold Belt. So again, the Chalcodene-Leichhardt belt, the Burstal suite, and the sort of Soldier's Cap volcanic interludes in here, as well as the Williams suite, all considerably more juvenile compared to this quartz 1610 quartz porphyry. What's also interesting is that the 1640 porphyry at Tommy Creek also sits in with the rest of the Eastern Fold Belt. So we've got a different source for the young porphyries compared to the older porphyries at Tommy Creek. So to try and put some of this together, well, what does this mean? So are we getting an indication here from Tommy Creek that we've got some sort of extensional or hyper-extensional rifting regime? So we have a magmatic association, which is often associated with rifting regimes. So the alkaline and the ultrapotassic rocks, the carbonatites, and our primitive mafic rocks. The shift in the magma source to more primitive in the younger rocks, so both the mafic, ultramafic at 1620-ish, and the younger porphyries at 1610 being considerably more primitive than the older intrusions. Does this suggest that perhaps we're getting a late stage upwelling of mantle causing partial melting at depth, or perhaps we're seeing maybe a delamination of the asthenosphere as the crust has been extremely attenuated after what's probably the best part of 200 million years of rifting. So does the Tommy Creek beds and the Milo beds represent a post-Soldiers Cap equivalent rifting phase, or is it a continuation? I don't think we can really say between the two. And I think it's probably worth comparing this to the similar sorts of conclusions that Karen presented here last year on the Soldiers Cap group way out to the east. These rocks are still younger than the Soldiers Cap group, so they're 1650 to 1625, although they're not as young as what some of the previous interpretations may have been. And we look like we have a possible disruption to this at 1640. So we have our switch in sedimentary character as well as the intrusion of these porphyries in at about 1640. And this roughly lines up with the Riversley events in the Western Fold Belt as put forward by guys like Betts and Gibson. So these actually true superbasin, true ISA superbasin equivalents. And are we looking at evidence for full mantle breakthrough? Was just around the corner, and it was halted by the compression of the Eisen orogeny? Or was perhaps that delamination of the asthenosphere the trigger for the compression episodes of the Eisen orogeny? So in summary, the Tommy Creek domain, well, it's even more complicated than we first thought it was. It's multi-phase, multi-source magmatism. We've got carbonatites and alkali magmas and all the alteration that seems to be associated with that. I think it's shown that detailed geochron can have huge value when you couple that with some detailed mapping, and that there's often a lot of nuance that we miss when we look at our larger scale geochron efforts, which sort of justifies the additional sampling that Ian and Laurie Hutton have been doing over the past 10 to 15 years. We possibly have a hyper-extensional regime being represented here in the Tommy Creek rocks prior to the Eisen orogeny. There's some other ramifications here that we don't have time to talk about, such as with such thin crust, we have high heat flow and the geothermal gradients. Maybe this explains the metamorphic conditions at Tommy Creek, that despite being at the top of the stratigraphic profile, we've somehow managed to get them to 630 degrees during metamorphism. And then associated with those high heat flows, fluid fluxes and mixing of sources. And we also have evidence for, and is probably linked to all of this, lots and lots of fluorine. We've got mobile titanium, rare earth and yttrium floating around. I've got niobium alteration and other weird things happening in the lithogeochem. But that's going to have to be a story for another time.
Thanks, Alex. Some weird rocks. Any questions? Well, I've got one. Mm-hmm. What are you going to do next?
So we do have lots of ideas. So what I haven't talked about here is the fact that we did successfully drill quite extensive sulfide alteration systems with low-grade copper mineralization. That doesn't show any particular affinities to our typical Cloncurry IOCG style mineralizations. Still unsure as to exactly what's going on there, but we feel like it's probably not typical IOCG. We have some more ideas, as well as some completely left field thinking that we'd like to test in the future. So maybe in a year or so's time, maybe we'll have some updates and maybe some success.
I will pester you then for another talk.
Just got one more from the floor.
Hi, question about the zircons in the carbonatite. Were they under photoluminescence? Were they nice euhedral, or what do they look like?
Yeah, so they were stubbier than I was getting out of the felsic rocks. But yeah, they were nice and euhedral. There wasn't any suggestion of rounding, which you did see in some of the marbles, but small. Interestingly, the bulk rock zirconium concentrations in the marbles and the carbonatites were quite similar, sort of around 50 to 100 ppm. but I almost always was successful in extracting them out of carbonatites and not always out of the marbles.
I'm going to ask a question again, but then Karen, you said you had zircon in rutile.
Yes.
Early on in the talk, but they were very, very small. What was their morphology?
Very difficult to tell. There were basically just spots on the SEM.
Were they? They weren't long, skinny exsolution style?
No, so we're talking about grain sizes around a micron.
Okay.
Or smaller here. And some of the rutiles themselves had weird compositions. So these are really rich in niobium and yttrium rutiles, some of these, and themselves weren't particularly crystalline. They were more like glass fragments,
okay,
rather than nice crystalline needle-like rutiles.
Over to Karen.
Fabulous piece of work, just fascinating. Lots of really good information coming out. And I'm curious about, so if the rocks got to 650, do you have any constraints on the pressure and how deep they were at that time, and or how much of an overlying sequence might have been deposited on top of that?
Yeah, so the graphite schists probably give us our best clue. So that 630 degrees was determined by Raman spectroscopy on the graphite itself. So that's a graphite crystallinity temperature, which is also consistent with the fact that we see all three kyanite, sillimanite, and andalusite within these graphite schists in various places. So you have andalusite, which looks like skeletal kyanite, and you also have extant sillimanite. So I think we're probably sitting somewhere around that triple point, which from memory is 3 kilobar, I think.
Metamorphic petrologist's dream.
Yes.
Sounds good.